Hello students, in this lecture we'll find another form of differential of a function at a point. We have in the previous lecture uh, we had discussed the differential of a function at a point or in an interval, which we had discussed in class also. That was known as first principle. Now we'll give it some generalized form of differential of function at a point of one variable, and then we'll generalize it in the generalize it for derivative function for several variables in the last chapter of this book. Function of two or more than two variables. In function of when we discuss the limit quantity differentiability of the function of two and more than two variables. Now let's define definition of the differential function. A function y is the function of x in the variable is said to be differentiable at a point x belongs to the domain to any point which is goes into the B if it is finite. If it is finite and determined in the neighborhood of a point, it is finite, it depends on the point. Y is equal to y plus delta y is equal to f represent x. Subtract first from second, we got delta y is equal to f of x plus delta x minus f of x, where delta y is the increment in the function corresponding to any arbitrary assigned increment in delta x in x is expressed in the form of this. So delta y is equal to f of x plus delta x minus f plus is equal to a into delta x, a into delta x plus epsilon into delta x, where a is independent of delta x and epsilon which is 0 as delta x approaches 0. So this is the differential of a function. This is the another definition of differential of a function fx at the point x. The function fx is said to be differential at a point x of the domain of function if in the neighborhood of that point this expression holds to fx plus delta x minus fx is equal to a into delta x plus epsilon into delta x, where is independent of delta x, and epsilon tends to 0 as delta x approaches 0, 0. This is the definition of derivative. Now we'll prove the theorem based on this. The necessary and sufficient condition for a function fx to be differentiable at a given point x acknowledging the domain of the function is that the function fx possesses a finite derivative at that point. If function had derivative, then derivative finite. If the derivative finite, then function differentiable at a point. Now we use this definition, necessary condition, necessary or if part, let fx is differentiable at a given point x should belong to the domain of this function fx. Then in the neighborhood of the point x, we can write for differential, then we will do point. This expression holds to f of x plus delta x minus fx is equal to a into delta x plus epsilon to delta x, where a is independent of delta x and epsilon is 0 as delta x is 0. Now, first equation, divide both sides by delta x is equal to fx plus delta x minus fx upon delta x is equal to e plus epsilon. Now, taking limit as delta x is 0 both sides, as delta x is 0 of fx plus delta x minus fx upon delta x is equal to is constant, epsilon is limit of constant as delta x is not here, so limit of is a, and epsilon to 0, the definition of divisibility, epsilon 0 as epsilon delta x is 0 is equal to 0. Now, this is the definition for derivative of point x given with first principle, so a comes out to be f plus x. F a is equal to delta x, so this implies fx produces a finite derivative a x. Substitution condition, let fx produce a finite derivative f plus x at x, then fx produces a finite derivative. So then f plus x will be the next definition by first principle. F plus x is equal to limit at delta x is 0, f of x plus delta x minus fx upon delta x is equal to f dash x, which is finite. Now, if we remove the limit, delta x means this is the value of function at x, this is your expected x, so there is some change in value. Change in value, if you remove this from here, so means this function minus this function of delta x minus this will be epsilon. Epsilon as delta x is 0. If you remove this, if you take the limit that x is 0, 0, that x is 0, that x is 0, so this will, you will get the same definition, that is 0, this will be f dash x, and this is equal to f dash minus f dash root 0 root 0, this identity holds true. So that term 0 as you got it. Yeah, when we remove the limit from here, we remove means we are not putting the point x from x to that x. So difference of this minus this comes up is very small, and this epsilon epsilon will put 0 as well as 0. So this is equal to now now multiplying both ways with delta x. This is equal to f x delta x minus f x is equal to f delta x delta x plus epsilon to delta x, where a is equal to f dash x and is independent of delta x and epsilon at 0 as its input. This implies f is differentiable at delta x. If function differentiable, if function differentiable at a point of the domain, then f dash is finite. If f dash is finite, then f is differentiable at the points. Both the definition, first principle and the definition which have defined in this topic are equivalent. Now let's see the box. If fx is differentiable for every point x in a closed interval ab, if function f is differentiable at every point of closed interval ab, and f dash a and f dash b, derivative of f at a, derivative of f at b are both opposite sign, then there exists at least one point x not belonging to the interval, at least one point interval closed interval ab such that f dash is 0. Now, what this implies? F is differentiable. Differentiability implies continuity. If it's differentiable every point means f is differentiable every point means this function is continuous in this interval. Continuous in this interval. Differentiable means if f is differentiable at every point this interval means they are the endpoints, and f dash a all the f dash a has some value, f dash b has some value, some real value. So because we are studying this book real world function, so f dash a is they have opposite sign, so means uh, between the value which f dash a has and f dash b have all the values, because all the real number values exist between this and this, because f is differentiable at a and f is continuous. So without loss of generality, we assume that one of the two, if they have opposite sign, let's do that. We can suppose this is less than, this is greater than, or we can this f dash a is greater than, or this is less than. They are real numbers. Put now this is definition of this is a first definition f x x plus delta x minus f x over delta x. If you remove the limit, we will have a differential value which will suppose here to be equal to equal to now let's suppose this is a function of x and delta x at the level of x. Now fx is the differentiable for interval. Differentiability implies continuity. F is continuous interval. So consequently, this f of x delta x is constant interval for integral. Since f dash a and f dash b have opposite sign, and since this sort of continues the Gaussian interval for that x equals to 0, so fx vanishes at some point x not between. Got this point? How this is possible? Now fx is continuous. It's continuous. This push out all the way. All the way. So the opposite sign is the fx function is continuous from A to B. So f dash a and f dash b are real number. So if x belongs to this, then all the real numbers in f dash a and f dash b exist. They have to be signed. Therefore, at least will get at least one x not belonging to the interval, belonging to the this interval to AB such that um, f dash a to this is penetrated point. Now school 0 f dash penetrated point. That's not is there. Taking limit delta x is 0 is equal to f dash. If fx vanishes in vanish, sorry, fx is the derivable in closed interval and fs is not fs, then there exists at least one x naught long distance interval such that fs is equal to fs x naught equal to 0, where there is any real number lying between fs, right? So if they are not, if they say they are real number, they are not, they are equal, then if f is derivable means f is continuous. If is derivable in the interval means constant derivable means f is continuous interval. So there is this at least one x naught. At least there how many x naught lies in them? Infinite. So at least one is there such that and then this would be a. Means uh, f dash a, if you take x from this closed interval, so just have all the real numbers f dash a. That f dash a is going to be f dash b, and fx is derivable in the closed interval, then f dash a pass from cannot pass from a value a without taking all the intermediate values. This means that f dash will take all the real values between a and b